So, good. So good morning, everybody, and welcome to another session of Earth to Class. This is our 199th. And we're pleased to welcome back Suzanne Straub, who's going to talk to us today about a link between explosive volcanism and the Earth's climate. First, we're going to take a few lighthearted looks at how people view volcanoes. Problem with everybody muted is I can't hear the roaring laughter. So who is this, Chris? I don't know.
It's from Lord of the Rings.
Oh, okay.
And he's at that point he's saying one does not simply just walk into Mordor to return the ring. So it made a fantastic GIF for the rest of the world once they started doing this.
He was the ranger, was he not?
He was a Boromir. He got killed after first.
I was told I'm not allowed to watch it because Frodo doesn't have blue eyes. He's not in the books. And just for your info, not everybody who goes into a volcano stays in a volcano.
Mike, when you click on a link, it opens another window. It might be behind your presentation.
Okay, I'll get rid of that now. So now let's get down to the science part. All volcanoes are dangerous, but some are more so. Volcanologists describe the power and effects of an eruption by the volcano explosivity scale, or similar terms. So this shows a bit of a comparison of some of the volcanoes. Pinatubo in 91 was 5 on the scale. Krakatoa was a 6. Yellowstone was an 8. This is a chart that shows more information about this explosivity scale. Here's another view. Mount St. Helens in 80 was just about a 3 or a 4. One of the others I want to tell you about is Tambora in 1815. This led to what's called the Year Without Summer in 1816, as many of you know. And one of the results of the Year Without Summer was a book called Frankenstein by Mary Shelley Wollstonecraft. She and her husband and cousins and friends were vacationing in Italy in 1816. And it was the coldest summer they had ever had. So the friends decided, since they were all writers, to see who could come up with the most scary novel. And she created Frankenstein, which of course led to many great movies like Young Frankenstein. Second point I want to make has to do with one of the major factors that creates climate changes, and that's the Milankovitch cycles. There are several Milankovitch cycles one of which involves the eccentricity of the Earth's orbit. Sometimes it's more rounded, sometimes it's more elongated. Second one has to do with the fact that the Earth's axis wobbles like a top. And the third is that the tilt of the Earth varies from about 24.5 degrees to 22.5 degrees. We're at 23.5 degrees right now. So when these things sort of line up, like the Earth is closer to the sun, which is about 100,000 year cycle, and the Earth's tilt affects how much sunlight is being received at various locations. And the precession also affects this. We have basically about a 19 to 24,000 year cycle, 41,000 year cycle, and 100,000 year cycle. And the result of this is that we see various changes in average temperatures and many other factors. One of the ways we're able to detect these is another view of the Milankovitch cycle data. We can see this in dust, and we can see this in some of the geochemistry factors that we're looking at, like oxygen isotopes. If we have volcanic eruptions, for example, in the volcanoes of the North Pacific, they may be carried by the ocean currents and settle down far away from where the volcanoes are. And then with scientific ocean drilling, it's possible for us to collect data which we can learn more about. I have some links here for you to look at your convenience. We're not going to take the time now to do that. Let's talk a little bit about proxies. These are types of evidence which do not make an actual measurement, but which can give us information. We can tell about changes in sea level. And we can use ocean sediments and the materials in the ocean sediments to tell something about climate in the past. We can use ice cores. We see annual layers called varves in ice cores. And the ice cores can trap air so that we have gases like carbon dioxide and the oxygen in the air. We can use isotopes in the ice cores, oxygen 16 to oxygen 18 ratios. And we can also do carbon dating of sediments. Some other types of proxies include corals, tree rings, pollen, microfossils, more than macrofossils, lake ice duration, and many of these are for local climate change rather than global climate change. But with ocean sediments and ice cores, we can tell something about the global changes. This is a picture from the National Snow and Ice Repository in Boulder, Colorado. Shows an example of an ice core. And every once in a while, as these things come in, they have ice core processing parties. As you can tell, the temperature of the room is fairly cold, so they dress up nice and warmly. One of the best places we've been able to get information about climate in the past has been on board the JOIDES Resolution. I know a number of you have heard talks about the JOIDES Resolution before, but in the next picture, you're going to see something you've never seen before. Me on board the JR. This looks like we're at sea, but we're actually tied up at a dock in Curacao in the Caribbean. This is what the bedroom looks like in the JR. There's 2 people because on board the JR, there are 2 shifts. People work 12-hour shifts. So there's always something going on. I don't think I ever met the guy who was in the room, in the bed above me, in the 10 days we were there. This is some of the equipment on board the JR. When the cores come up, they're placed first on here, and these are some of the other teachers who were in the program with me, looking at a sample core. This is an example of a core when it's been cut. Black usually indicates a lot of organic matter, and brown may indicate various types of sediments. There's very strict protocols to describe these. So here's an example of a description of one of the cores. And as I said, there's extremely defined versions of what is in each sediment. This is looking down through what's called the moon pond, or moon hole. This is an opening in the middle of the ship where the drilling rig goes down through it. Here's some of the cores, some of the teachers. This was an international group. This is Jean-Luc Béranger from France, who's one of the most active teachers in Europe. And this is just a list of some of the ideas that we came up with during the what was called School of Rock program on board the ship. We were allowed to pick over some of the cores. These are some of my colleagues. This is a guy from New Jersey. And a couple of last cartoons. You can tell geologists are in love if they ignore lava right next to a wedding dress. Okay, so I'm going to stop sharing my screen. And are there any questions? Okay, so let me welcome Talia and Doug. Suzanne?
Yes.
Talia here is a 10th grader in high school, and she's hoping to get an internship at Lamont. So I know she's got a meeting later today, a Zoom meeting with Dallas.
Yes.
She's been coming to class since she was in 8th grade. Doug is a chemistry teacher at the Bergen County Academies. Okay, and I don't know if I mentioned Ruben to you before, but Ruben is a New York City educator. Okay, so Suzanne, take off.
Yeah, thanks a lot for this introduction, Mike. We are going to touch again if you share a few things. We are going to do that. So, oh my goodness. Should always be at the beginning. Here we are. So I hope you are all muted, but I hope also you can hear me. So today I'm going to talk about the link between explosive volcanism and the Earth's climate, whether it exists, starting with this beautiful eruption of the Anatahan volcano in 2003, which was photographed from seas in the Mariana, south of Japan. I first come back to that picture Mike showed before, the volcanic explosivity index, VEI shortened. It's a measure of the magnitude of an eruption. And it's important to remember, as the magnitude goes up from 0 to 8, these are not just one single step. Each time, it's a logarithmic scale, so each time it goes up 10 times, or from 0 to 1 is up 10 times, and then 10 times more to get to 2, and from 2 is then 10 times to get to 3. So it can get pretty large in the end when it reaches the largest known eruptions known around 8. And the other thing to keep in mind, it's in the volume of the erupted tephra by which it is measured. So we go out and measure these tephras in order to get the size of the eruption. The term tephra is basically identical to the term volcaniclastic. It describes broken volcanic rock that was generated during an explosive volcanic eruption. So the first thing I want to do is also to go a little bit through these volcanoes for eruptions we had, which are historically well known, and what effects they had. Only 10 years ago, we had a fairly small eruption from the Icelandic volcano Eyjafjallajökull, and that created a lot of havoc. It was a fairly small eruption on the explosivity scale, on the size 4, but it did generate an ash cloud which went all over, part over the Europe, and shut down effectively the air travel. I think some of you will definitely remember that. It left tens of millions of passengers stranded for a few days, and it was a considerable economic loss. I don't think lives were lost, but it shows the power of how a fairly small eruption can disrupt our civilized life on that planet. The next one I want to talk about is Mount St. Helens. It's 4 straddling 5. That was the 18 May eruption in 1980. There was warning of that eruption. The people knew that this volcano would erupt. They closed the zone off, they monitored it, and yet 57 people died, and it created lots of 1,000 animals was killed, and lots of homes and railway was destroyed. For the simple reason that the violence of this eruption was underestimated. What we had not counted about was that this mountain is just going to be blasted apart. We thought it would be something more like this, an end, and then the mountain was blasted apart and caused all this damage. Only 4 to 5, still fairly small. Mike also mentioned Pinatubo in 1991. It's next magnitude. It's a little bit larger on the scale. It was the second largest eruption in the last century. The largest was, by the way, Katmai in 1912. And I do mention Pinatubo because it had a measurable effect on the climate. So what happens here is, in this cartoon, I found somewhere, I Googled somewhere out, but the volcanic ash is very rich in sulfur. It breaches it goes into the stratosphere, reaches the troposphere at about 10 miles high. And then the sulfuric drops and aerosol that distributed into the atmosphere and just prevents the sunlight from reaching the Earth's surface. On that picture here on the upper right, you can see the sulfuric cloud measured by satellites, that this was distributed in the aftermath of that eruption around the globe. There was a measurable degree by 0.7 degrees Fahrenheit globally, and caused also a temporary effect, a temporary distraction of the accelerated distraction of the ozone in the atmosphere. So it's a very measurable climate effect. Fortunately, they were still short-lived. After a few years, this thing was over. So the next large eruption, this was Krakatoa in 1883, which is a volcano located in the Sunda Strait between the island of Java and Sumatra in Indonesia. You see these small little sinks here. That's the present Krakatoa volcano. And this insert here, it shows the island, how it was before the 1883 eruption. This part of the island was blasted away in a huge sonic bank that was heard in about 3,000 miles in circumference, as shown here by that green circle. And it also caused a huge tsunami that killed far more than 30,000 people on the surrounding island, on the surrounding land here. And that was in 1883. The area is much more populated. And you might remember that only 2 years ago, in 2018, a collapse of the small island here in the middle, the Anna Krakatoa, the child of Krakatoa, the newly growing Krakatoa, caused an acid tsunami, and many hundred lives were lost, and more than 10,000 people were injured by the resulting tsunami to that island. Again, this eruption caused global temperature a drop in temperature, and it is also well known for the beautiful optical effects. It was sunsets globally for years that were really red, so the sky was aflame. Even fire brigade was called at some location because they thought something was burning, but this was the effect from the ash in the atmosphere, and many contemporary work of art still show that. There's a good memory of that eruption. Mike also mentioned, yeah?
I could jump in for a moment. One of the artworks that was inspired by Krakatoa's impact was a very famous painting called The Scream.
Yes, it's thought to be related to this red sky showing on that scream is thought to be inspired by these sunsets from the Krakatoa eruption by Edward Munch that made that painting. That is also related. So it was there. It's not only a local phenomenon, we see the effects globally of these eruptions. Tambora 1815, a little bit earlier, the most powerful eruption in human history, and connected with a year without summer. For example, here in New England, there was snow and frost in June of 1816, the year after, and it caused failed crops and famine in the 3 summers afterwards worldwide, simply by the amount of the ash and the gases that went into the stratosphere and block out the sunlight coming to the Earth's surface. I was famine, many people died, diseases spread, and there was a huge direct and indirect human death toll mounting into the 100,000s from these eruptions. And you see, and the upper part is also the ash fallout that can be measured in the sea. 100 centimeters close to the location, 1 meter, but still on Borneo and many hundreds kilometers away, there's a perceptible layer of ash distributed very far away, a huge crater where this volcano is located. But still, we are only at 7. Let's go to another one. This was prehistoric, the Oruanui event in New Zealand. New Zealand has a very active volcanism on the North Island still, and the Oruanui event 26,000 years ago, before the last glaciation, was one of the biggest events known. You see this down here is a North Island. It's a little bit smaller than New York State, the area, maybe 20% less. And this is a simulation of the eruption cloud of this eruption. And you can be sure that anywhere on this island where you would have been, you would have seen that eruption cloud reaching the stratosphere. It caused an ash fall. That means that ash that has enough momentum to be propelled into the atmosphere and spread out through the airs. It's still almost 20 centimeters thick on Chatham Island, more than 1,000 kilometers away. It covered, the ash alone covered most of the North Island and much of the South Island. It also caused an ash flow, and these ash flows are generated when the ash does not have enough momentum to fly through the air, but this whole eruption column collapses, the ash travels on ground very fast, very dangerous, and it caused a cover of 200 meters thick on most of the North Island. This is definitely not a place to be around when such eruption is going to happen. And they do. I speak now of the biggest known eruption the geoscientists know. That was the last one, when the Toba Caldera on the island of Sumatra formed about 75,000 years ago. It was one of the largest known super eruptions. You see on a photo, you cannot even show any longer this huge caldera this eruption has left behind. The lower left side shows the ash fall. I'm showing this. This is a centimeter sized here. So this is 100 centimeter close to the eruption site in the Indian Ocean. The ash was in centimeter size, still present here in Africa and up to the Himalayas, borne out towards the west by the wind. The event was a global ecological disaster. It's still debated how much it really what it really caused. 10 years of global volcanic winters, and it maybe have affected 1,000 years of global cooling. We know that these eruptions happen. They have happened in the past, and they are typically associated. This is a map of global volcanoes where you can have more or less large eruptions. And the most dangerous one and the most frequent one are associated with subduction zones. This is shown here in the upper left two sides, where one plate, lithospheric plate, is subducted beneath another. And basically it's a whole Pacific rim. The Pacific ring of fire is made up of subduction zones. And here are these very dangerous volcanoes are located in abundance. We know they have really violently erupted in the past, and there is no question they will do so in the future. Just to mention, we have also a few volcanoes, very large volcanoes not related to such a subduction volcanism. One is the Yellowstone. That's a different one, but it also can cause super eruption. Another one is that caused the Long Valley caldera. It's also an old ancient site of a super eruption. But again, the most frequent one and the most abundant one are those in subduction zone. Indonesia is also in subduction zone, where these big Krakatoa, Toba, and are located. New Zealand is definitely one, and we know it's coming, it's there. What we don't really know, have these volcanic eruption, are these a climate player, like other mechanisms, like the Michael which cycles Mike mentioned. Is there anything, do we know that the cumulative activity has a long-term effect on the climate? And for example, can volcanic eruption not only force winter, but also initiate a global glaciation? Or is the effect short-term? What happens, we know that if we pump sulfur into the stratosphere, that we deflect the sunlight, but we can also add CO2. This is a climate active gas. It would cause a different effect. It would lead to warming. And we know perhaps that one eruption has a fairly short-term effect in geological time, but even if you have a cumulative number of this eruption, and perhaps even the timing of the eruption, together with the other parameters that shape climates may play a role. So how can we as geologists investigate these links? And for this thing, we need a geological record through time. And it's a fact that this record does not exist on land simply because of erosion. Volcanoes look awesome, but essentially, geologically, they are unstable, they are crumbly, they erode. You see, it's not a big thing. This happens in a geologically very short time that the volcano is eroding away, so we don't have any information on the strata. These little channels here form very rapidly into a pyroclastic ash deposit after eruption. And a few years later, it might look like that most of this is eroded away or overgrown. So on land, we don't really have a chance in getting a good geological record through time, and therefore we go to sea. So what happens if we have an eruption show here in that cartoon? The cloud spreads out, the ash falls down. Ash is just small volcanic particles less than 2 millimeter in size, and they accumulate in marine ash beds. And in the marine environment, the strata accumulate, it's not as erosive, and then if it accumulates over a long time span, we can go here and visit drill ships and can extract cores from that in where the ash layers are contained. So don't look at the mid-ocean ridge, imagine here an explosive arc volcano, and think here is the ash accumulating. I have here a picture of a typical drill core as it comes out from the ship Choice resolution. Here on the left is a scale in centimeter. The overall length of a full drill core is typically around 9 meters. And then the cores are being cut up in 1.5 meter lengths in individual sections. And then accumulate, this picture is accumulate picture of 1 9-meter core. And if you look closely, you see this thin layer, centimeters thick of dark and light. Here is an enlargement of a light layer. You have this light stuff here on top, but the ash layer is a small discoloration here below. It's only a few centimeters thick. And that's what typically causes, it's caused by an explosive volcanic eruption. They are visibly there, they are instantaneous volcanic events, and they are datable. So we can get the time out of it. There are various methods. I don't want to talk about the details today, but they can be taken with fairly good precision. And they are time precise event, and they form time series in which we can estimate to see whether there are links with the climate. And I should make mention here, usually by the time you need a fairly large eruption to make a discrete ash layers in the marine sediment. It usually starts around 5 eruption size. The smaller eruptions don't have the power to accumulate on the seafloor. They just are vanquished in the other sediment. So we know already, simply by the facts, we have so many ash layers accumulated in the course of a series of large-scale eruptions through time. So I have found this map, many things of the maps I'm showing today, I just Googled. And I show this because of this yellow area, because it gives an approximate impression where we find sediments that are rich in volcanic ash. Of course, they are usually associated with a specific ring of fires. We have the best occurrences, but you see, if we go out and if we go drilling, then we have a good idea of getting such records. And how can we relate that to climate? I open here just one slide and the next one, and a side box, so to speak, and explain the the climate signals. Mike has already done this, but again, I just recapitulate. Here on the left side is a graph showing the last 4 million years in history. A very important date to remember is about 2.58 million years. This is the begin where we had on the northern hemispheres, we had the waxing and waning of ice sheets, where the Earth had cooled down. It was a little bit hotter before. By this time, it cooled down to the times that we sustained ice sheets, and these ice sheets waxed and waned through time. There were periods when they increased and periods where they decreased. And as you all know, we are right now in a period of ice decline, which gets artificially strengthened by human interactions. That's the last interglacial, that's the so-called interglacial, and the glacials are also cold. And that's a signal that is found in sediments worldwide by a range of proxies that had Mike shown. One of the most important proxies is Delta 018. And we find that signal in all global sediments, Kansas extract by proxies. And you see, in first time after the start of the ice cycles, it has a 41,000 year cyclicity. That is here, which is the one of the obliquity. That is one of the Milankovitch cycles. And then around 1 million years or so ago, there was a transition to the eccentricity cycle becoming dominant in the signal. That's around 100,000 years. Again, we know from the global sediments, the signal is everywhere still. It's in the sediment proxies, and it is definitely proof and a strong indication that global climate is affected by the way, our kind of Earth works way around the sun and how it's wobbling around in space. It's very sensitive. So all what we have to do at this point is to investigate whether the ash pits also show such cyclicities. And if yes, is there a causal link to climate evolution? Seems to be very likely. We are in the middle of doing that investigation as geologists, and right now we have two really key observations. One, it is in the wake of the drilling program, we found that at 2.5 million years, here he has his little black arrows, this is his aura, and these black ones are ash layers, they do increase. Again, here at 2.58 million years, this is a number of volcanic ash zones found in ocean drill cores. It makes a huge increase with the beginning of the Quaternary age. It's the age, the Earth age, which started at 2.58 million years. And we know that this is a very strong signal. You see these drill cores, 882 and 883 were taken here at the end of the Emperor chain outside Kamchatka. And 887 here on the right was drilled closer to the US mainland. But all cores show this very characteristic and typical increase of ash layers at the beginning of the Quaternary. And so that suggests that there might be a link to climate. We still don't know. So that was one observation. The second observation, we know that these ash beds in the Quaternary during the last 1 million years about that show a cyclicity. And this is an Asaitopy drill hole south of Japan somewhere. And the blue ones are the ash layers. The red one is the delta O18 curves, and you show this, that is a very detailed analysis of the ash layers. It shows that it's cyclic. So, and then we can do an analysis that is called spectral analysis. And the red one, we know that is the climate signal of the sediment. It shows 100,000 year cycles. It goes up it shows a 41,000 year cycles. And it shows also a weaker signal of the precession cycles, which is around 20,000 years. And in the sediment, these signals are really there. And this was an ash profile that first showed that at least 100,000 year cycle here in the ash bed, it is also there, as it should be there here in the last 1 million years of the Earth's history. This was the first proof, this study, that we have also this Milankovitch cyclicity, and orbital cyclicity is also reproduced by the tephras. So that we know, and that we are. So these are very intriguing observations for us in geology. But now we need a couple of more cores with ashbed series to test whether this is true. We need cores that encompass this entire period of the last 2.58 million years. We want to see whether this is true from the high latitudes, where the effects of the glaciation are strongest versus the lower latitudes. We want also to study different arcs with different crustal basements and may differently react to the glaciation. Simply, we need more information. So we have the ocean drilling program. And this is a map that showed the holes that have been drilled into the ocean floor. This drilling program started in the late 1960s. It's going on now on 50 years or so. There were 2 ships in the drilling program. The upper one panel shows here Glomar Challenger, that was before my time. And the current one is a Joyous Revolution on the lower panel, which is currently sailing in the South Atlantic. And you might think, wow, we have a real lot of cores, and we should be able to find a couple of that have these tephra profiles, but amazingly, it's not that different. You know, this is going on since a long time, and in the early days, the technique was not that major yet, and the cores were, for example, not continuous, and they were disrupted, and we didn't have the techniques to investigate well. We didn't have the techniques in investigate the sediments and so on. So in order to find a really good drill site, we have, for the tephra studies, we have to have multiple criteria. We need, importantly, continuous recovery of undisturbed cores. And we have really, in the last 15 years in particular, we had a huge technical progress in the coring technique. So we can make sure if we drill into the sediments, we get 100% recovery and not a core that is disrupted by many holes. This is not good for this kind of study. We need also a dating technique for that core that is on the scale of the ice cycles. There are many core dating techniques. There's many different resolutions. It's good for the one purpose, but for that one, we really have to have a really good high resolution core, high resolution H profile for that. We need also a suitable background sedimentation rate, but not so high that it might overwhelm the ash signal. Can imagine if you have a very high sedimentation rate, the volcano deposit never makes it through to be a discrete layer. And we also need to be in an area with a regular ash input. So for this project I'm working on now, we found site 882 located in the Northwest Pacific, outboard Kamchatka and the Western Aleutians. The site has been drilled already in the 90s, but we were lucky. We had a full recovery. The site, the tephra layers were recorded in a first pass on the ship itself. We know that it increases again on this important 2.58 million years boundary. We do have the increases. So the course is reaching through the last 2.5 and 2.58 million years. We know already from some preliminary investigations that most of the ashes are likely coming here from Kamchatka. These little circles here, they show on the size of historically known eruptions. So the larger this white circle here, the larger the historic eruption here, and here Kamchatka did have, is really a source of that produces eruption in the magnitude of 6 and 7. And we know that this is coming probably here. We might have a couple of ashes from the Aleutian. We need to investigate this layer to show us. But given the dominant wind direction, it's presumably coming here from the west. Possibly even large eruptions might even deposit ashes here from Japan, northern Honshu, and Hokkaido, especially here down in Kyushu, have really areas with really devastating large eruption, and widespread tephra are very well known. So we had a couple of preliminary investigations on that core. And Mike mentioned people, scientists sail on shore its resolution. They usually stay there for 2 months. I have been on these trips myself. These are very intensive 2 months, and we usually, the core gets out, scientists scramble to describe to get a first order of that, what it is really is. And then here, so the first pass with the age profiles, the ages that were obtained on board. Again, in red, this is the sediment reference course that can be linked to the orbital cycle. You see the ashes are not really there. They seem to be close enough in the 41,000 year cycle, but it's a little bit too much to the right. It seems to miss there is a short-term cyclicity, but it seems to miss really the 100,000 year cyclicity from the orbital cycles. So what we do is now we use a more recent and better age model. And I also went back this summer to Texas, and I traveled to the core repository where this core is deposited, and I did a redescription of the ashbed series just to make sure nothing was missed, because on the shipboard, as I said, it's very stressful. You really scramble to do the basic most thing on the course, even if you work 12 hours shift for 7 days a week. It can be a very hard job. So, but these cores are being brought back on stores, on land, and they're being stored in repositories for scientists to be able to access this. And this was now about the time doing that at core, and that's what I'm doing. And right now I'm looking on 3 possible results. One is that the volcanism is unrelated to climate. We see cyclicities in the volcanism, but it's not controlled by the orbital cycles, by the Milankovitch cycles, but on the other cycles, and then we need to figure out which ones. And there is a possibility that we find a correlation with glaciation, with the glacial cycles, but then we have to ask ourselves whether the volcanism drives glaciation, whether all this, what it brings out into the stratosphere, it's really helping deflecting the sunlight, making Earth cooler, promoting glaciation. There's also the ash is also falling into the ocean itself, and it causing the algae to bloom, and the algae consuming the CO2 and then taking it out of the ocean atmosphere systems. This would also cause cooling. But glaciation may also simply drive volcanism. There is another hypothesis around, which is very popular. You know, if the ice is lying on Earth, it's just suppressing volcanism. So if the ice is going away, it's going to thaw and going to get away, then it suddenly allows volcanism to come up. So this would be a very different cause and effect relationship between volcanism and glaciation, but we need to investigate this. I wanted to show you one core picture from that site. That's it's around this is the time when we enter. It's around 2.85 million years when we enter the glacial cycles. The one thing what we found in the course is a so-called drop stone. And these drop stones are released from floating icebergs. These icebergs have a lot of material eroded from land. And then when they drive over the sea, the drops this down into the sediment. And this is a so-called drop stone. We know that at this point of time down here, the ice was ongoing. And then a couple of 100,000 years later, we had these ash beds that shows a 19 centimeter thick, and it must have been an eruption. If it comes from Kamchatka, the most likely source is in the magnitude of 7. And I've seen many so thick ash layers in these core. So we know magnitude 6 and 7 eruptions are going to be very frequent here. So this is ongoing, and I hope that in the second lecture, in about 1 or 2 years, I will be able to show you what has been coming out of that, what we found, climate cycles or not. So, and this is my last slide. I wanted to say, to share about 2 resources. Mike already straddled the scientific ocean drilling. There are websites, and on these websites you can find a lot of education and outreach, including the School of Rock, including the possibilities for teacher to sail, including for class material. You can really inform you about this very important program, which is still ongoing and we hope is going to last. And the other thing is, I don't know whether you're aware of a movie that was released in this year, and it's a look back on the big Mount St. Helens eruption. I found it on the Disney Channel. If you have access to that channel, I'm sure it's also released as CD or something where it's a very good record of that, what a volcanic eruption does and how dangerous it is and what the effects are of even a fairly small eruption like Mount St. Helens. So, and with this, I would like to close, and I'm happy to take questions.
Thank you very much, Suzanne.
Yes.
Do we have any questions out there? If you've got your video on, raise your hand, please.
You need to unmute. I think you're muted.
Barbara, you're still muted.
Okay, am I good now?
You're good now.
Okay.
You hear me now?
Can extreme explosions affect the procession?
No, I don't think it works that much. At least I hope it doesn't. I would be a really disturbing thought if a huge volcanic eruption can actually affect that, but we have no indication for that because the precession cycle is really well documented in the sediments, and we have no indication that any of the major eruptions that we know has interfered with that. It would be a very disturbing thought. I mean, these volcanoes are powerful enough by themselves. So if the Earth starts to wobble following such an eruption, would be really, I don't want to think of it.
Barbara, you're a physics teacher. You can work out the mathematics of it.
I'm tempted. I'm very, very tempted with this. I have been thinking about it ever since we started talking about it.
Good.
Yeah.
Jim, you had a question?
Talia, yeah, but you need to unmute.
I was just wondering, is it uncommon to find drop stones in cores?
Yes, in the zones where the icebergs are floating, you find them fairly commonly. In that course that I showed, it was really accidental that the ash layer and the dropstone were there jointly. It's a nice a picture of showing that these two events seem to be related, but actually together with the ash layers at this point, at 2.58 million years, the dropstones have also increased. So we know that both the ash layers and the dropstone increased. That was an indication that climate and volcanism are related. So yes, if you would drill in the north where the icebergs are formed in the southern hemisphere, dropstones are very common. Not as big, they're usually smaller, and of course it can't be bigger than the diameter of the core, then the core is going to get stuck.
Thank you. Other questions? Renee?
Yeah, stop sharing. I mean, I think we recorded that, didn't we? Yeah. So if you have questions afterwards, or I'm happy to answer that. I should have said that most of the figures I showed, I Googled very quickly. I was a little bit not so good about tracing the sources, but essentially it was Googled. And I did wonder maybe if you have a couple of inquisitive students, you just put some Google about what happens in a big volcanic eruption. It's actually chilling if such a thing happens, what this kind of effect it has on humankind. And we still should remember there's nothing what we can do to prevent such an eruption. If you're lucky, we can predict it. We are talking about preventing asteroids coming, deflecting it from Earth. In the course of collision course from Earth, we are really tinkering with the climate. But if this basic force of the planet volcanism comes out with such power, we can only run and mitigate the consequences. And a planet that gets crowded now with close to 8 billion people, it's getting a big problem. It's personally, I'm a little bit frightened, and I won't be sorry not to see a very big eruption. It would have devastating effects. Yes,
Yes, Talia.
How do you predict volcanic episodes?
If we know what's, if they have a cyclicity, so in the geological time, we can this forecast into the future. And the other thing how to predict a volcanic eruption is monitor the eruption and monitor its fluxes. This is done with many volcanoes, but we can't do everyone yet. It's simply too much. And people I have a lot of colleagues here at Lamont who work very hard in trying to find means how to predict a big eruption, not the small ones, but a big and devastating one. We probably have enough warning. Whether we have enough room to move out of the way is a different question. We are very much aware of this danger.
Just for everybody's information, there's about 16 active volcanoes right now. Usually there's about 20.
Yeah.
But none of them are massive.
It comes fast. I still remember Pinatubo. That was fast at this point of time, and that was not that big yet. And it cost lives. It costs a lot of lives. People maybe not believing what's happening. It comes out in the moving of Mount St. Helens. There was a person not believing that he did not move out of this critical zone, and he died. We have also to think about this kind of attitude. I mean, if we should think that actually deglaciation drives volcanism, so that the release on the pressure on the Earth's crust is leading to an increased volcanicity, then, well, this is not a good result in terms of hazard management, because it simply means we need to be aware as the planet is now heating up that this might incite volcanism, also more volcanism.
I will add that 3 of the people who were killed on Mount St. Helens were volcanologists who couldn't get off in time.
Yeah, there was a volcanologist where now the observatory is, Dana Johnston. It was thought to be a safe point, but when the mountain just disrupted, he had not enough time to run.
So Talia, this gives you plenty of time to get prepared to become a volcanologist.
Yeah.
Okay, so we're at 11 o'clock and got just a few more minutes. Want to thank Suzanne again for a very interesting talk.
Thank you
And
for listening. Thank you for coming.
I will send out the link when Chris tells me that it's ready. And we'll put it on the Earth to Class YouTube site. So have everybody go there, build up our hits, or whatever it's called.
Okay, thank you very much. Great to have met you today. Any questions, just send them to me. I'm happy to answer.
Or
Have a good day.
I'll pass
Yeah.
them along.
Yeah, bye-bye.
Bye.